Hello class. The next addition reaction that we're going to look at is called an acid-catalyzed hydration. So what does the words mean? We're hydrating, so that means we're adding water across the double bond. And in order to get that to occur, we need to add a catalyst. So a prime example of this process would be you have your alkene, and you could represent this reaction in many ways, but I'll start off with just one for right now, okay? I'm going to just say we're going to add the hydronium ion. And when we do that, hydronium is basically when you take water, okay, and you add an acid to it. And acids can be represented by just a proton. And so that is going to generate our hydronium. So in order to generate that hydronium, what we typically do is we can write it like this. You can say, hey, we're going to add some water. And we're going to give a catalytic amount of sulfuric acid. And typically you'll see a little cat with an abbreviation for catalyst. You could also see it represented by this, put in brackets. That implies that it's the catalyst. But I like to use this method right here. Okay. So you could say, okay, this catalyst, sulfuric acid, can represent the H plus here. And so what happens when you take water and put in a few drops of sulfuric acid to it? You're going to generate the hydronium. You're going to get some acid solution. Okay. And so what happens when you take an alkene, put it in some water and a catalytic amount of sulfuric acid, is you're going to follow the Markovnikov rule. And we're going to add a hydrogen on one of these carbons. Where's the hydrogen? What carbon, carbon 1 or carbon 2, will you add the hydrogen to? Markovnikov rule says you have to add it to the carbon that has the most hydrogens. There it is. So we are going to add hydrogen there. And then by default, the OH is going to go there. Okay. Now, so this may not be making a complete sense quite yet, but let's just bear with me now, okay? So I'm going to, so this hydrogen right here is that hydrogen there. And I'm not going to draw that in for right now. So why is this called a hydration? Because what have we added across this double bond? We've added this hydrogen and that OH. What are those two together? That's H2O. So we've added water across that double bond. So that is an addition reaction. And these acid-catalyzed hydrations follow the Markovnikov rule. Now, why would they follow the Markovnikov rule? Well, it all comes down to the mechanism. So the mechanism is very similar to, what was the last reaction we did? We did the hydration, hydrohalogenation, yeah. The mechanism is very similar to the hydrohalogenation. So the first step is we have to understand that this combination of water and sulfuric acid is going to generate the hydronium ion. And I'm going to represent the hydronium ion like this. And the reason why I want to draw it that way is because it just makes it easier for the mechanism. So the first step is this alkene is electron rich. This hydrogen right here is electron poor. So it's going to grab it, break that, and then we are going to go and add the hydrogen according to Markovnikov's rule, right? So we'll add the hydrogen there. That will generate a secondary carbocation plus water. So you see how the hydronium get converted into the water. Now so the same principles for carbocations. Whenever you form a carbocation, can it rearrange? And in this case, it wouldn't rearrange because we're at a secondary carbocation, or a tertiary carbocation, very, very stable. So the next step in the mechanism is now our water is a weak nucleophile, and it's going to come in and attack the carbocation. And so I'm going to draw that down here. So when the water attacks, there's 2 hydrogens attached to it, right? But now oxygen has what? 3 bonds. So that makes that oxygen atom a positively charged species. And maybe we can draw this out as a bond. And we call this species an oxonium ion. Let's do that in a different color here. So when you have an oxygen attached to a carbon chain here, and it's positively charged, we call that the oxonium ion. Now this oxonium ion, because it's positively charged, that's not going to be the end product. Your end product is more often than not going to be neutral, because charged species are too high in energy and they're going to break apart, or they're going to react to gain more stability by becoming neutral. So what's the next step then to get that oxonium ion neutral is we're going to have water present, right? Not all of the water is going to be converted into hydronium because there's large excess of water and a catalytic amount of sulfuric acid. So when you have a catalyst, you usually don't have a lot of it. You don't need a lot of it because a catalyst is never consumed in a reaction. It's regenerated. So we have some water still, a lot of water just hanging around. So we're going to use that water as a base now to make this oxonium ion neutral. So we're going to come here and grab a proton and do a proton transfer step here to generate our neutral product. And more often than not, you're not going to be shown that the hydrogen was also added there. But look at what happens when the water grabs the hydrogen off the oxonium ion. What do we generate? We generate hydronium again. So we have just regenerated the catalyst, and this just keeps going and going. So that is an acid-catalyzed hydration of an alkene. And you can see that the mechanism, the first part right here, this mechanism is very, very similar to the hydrohalogenation reaction. Okay. So another thing to note is the rate of these acid-catalyzed hydrations. So what I have here are 3 different types of alkenes, and the difference between the alkenes is the substitution pattern. And what we're going to do is we're going to time how long this reaction takes right here at this top one. And whatever its time, we're just going to say, okay, we're going to call that a relative rate of 1. And then we're going to compare these other 2 to this reaction rate. And what we're going to find is that just by adding 1 alkyl group to this alkene increases the rate 10 to the 6 times. That's 1,000,000 times faster. It's crazy. And then if we add a second one, look at what this, it goes 10 to the 11 times faster. Can you look at the, so there's the data. Can you use the chemical principles that I've taught you up to this point to like rationalize why is this a thing? Well, it all comes down to carbocation stability, right? Look at this. When we have this guy, what does Markovnikov rule say is going to what's the first intermediate going to be? The hydrogen's going to add there to generate what? A secondary carbocation. But when you compare this guy right here, what do you have? You have a secondary versus a tertiary. So that tertiary carbocation is way more stable, so the reaction is going to go a whole lot faster. That's basically what it boils down to. Isn't that cool? So what's next here that we need to talk about? We can talk about equilibrium now, how we can control which direction we want it to go. When we take a look at acid-catalyzed hydrations of an alkene, what's interesting is that it is an equilibrium process. So what we have here is in the forward direction, we have the acid-catalyzed hydration. But in the reverse reaction, what are we doing? We're doing an elimination. Why are we doing an elimination? Because look at what we're eliminating. When we go from this alcohol to the alkene, what are we losing? OH and this hydrogen. You can see the OH is no longer there, and that one of those hydrogens is taken off. So what is that in reverse called? That is a acid-catalyzed dehydration. The removal of water. So could we also call this an elimination? Yes, we could. It's just this elimination reaction has a special name, and that's called dehydration. And in order to do this dehydration, we have to have an acid catalyst. So both these processes, there's some sulfuric acid present. So if you want to favor the alcohol, what you're going to do, let's make sure I get this right, you're going to have dilute sulfuric acid, H2SO4. There you go. So if you do this, if you take an alkene and place it into water, okay, and you add just a very little amount of sulfuric acid, and it's very dilute, then it's going to favor the alcohol. In contrast, if you want to favor the alkene, you are going to have concentrated sulfuric acid. Okay. So as we've seen in the previous reactions where they were temperature, we could control equilibrium by temperature. We can also control equilibrium by the concentration of our reagents. And it boils down to Le Chatelier's principle and how we can influence the equilibrium and where we want the reaction to go. Okay, so let's use Le Chatelier's principle to describe this. Okay, so let's say we have this reaction here, okay, alkane plus water. What we're going to do is add a very small amount of sulfuric acid, okay, and then we let it sit. And with that very small amount of acid, equilibrium is going to eventually be reached, okay? Once equilibrium has been reached, how can you now, from this point on, force it either way? So if you want to favor the alcohol, you want dilute sulfuric acid. So how would you do that when you've already added sulfuric acid to get the reaction going? How can you dilute the sulfuric acid? Well, you would add water. If you add more water to the reaction that's already at equilibrium, the Shotley's principle says, hey, you added water, so we need to go in the forward reaction to make this product, to get back to equilibrium. So if you want to favor the alcohol, you dilute the sulfuric acid by adding more water. Isn't that cool? But then the opposite is true, okay? What could you do here? If you want to, once equilibrium has been reached with a little bit of sulfuric acid, we want to actually now do the dehydration. What would you do? You would add more sulfuric acid. And what are you doing when you're adding more sulfuric acid? You're basically diluting the amount of water. So you could kind of look at it like, hey, you're having less water. So Le Chatelier's principle says, hey, you got to drive the reaction to the left to compensate for the amount of water that's being diluted down. You could also do this with distillation, and you'll learn about distillation more in your orgo labs, but distillation is physically removing the water. So if you have a chemical setup where it's removing water as the reaction's going, then you can drive it to the left. But if you don't have this fancy distillation setup, just know, add more water to dilute the sulfuric acid to drive it to the right. If you want to drive it to the alkene, then you add sulfuric acid and keep that concentrated. Okay? And that can all be explained by Le Chatelier's principle. Now, acid-catalyzed hydration can also generate stereocenters. Let's erase this. Do you recall when we were looking at hydrohalogenation, where if I had this reagent right here, this hydrochloric acid there, remember that reaction? And we have this regiochemistry that we have to account for, and that's explained by Markovnikov's rule. But then we have two different stereocenters, right? We have our R and our S. And when we do this reaction, we get a mixture of these products, right? Remember why that was? It was because the intermediate right here is what? sp2 hybridized, so it was flat. And so you remember how it was actually drawn this way. Remember how I looked at it like this? Right there. And then you have the p orbitals right here. And so the chloride could attack from this side or this side with equal probability. Remember that? Well, that same concept applies for acid-catalyzed hydration. If you have water with the acid catalyst, sulfuric acid, like that, what are you going to generate? You're going to generate a mixture of alcohols with different stereocenters. It's the same principle, because what are we generating? We are generating a carbocation. And so then what's the next principle that we have to watch out for? Rearrangement. So even with acid-catalyzed hydration, you have to worry about the stereochemistry and rearrangement. So if we change this problem up a bit by just adding this right there, we would have a mixture of these, but then what else would we introduce now? We would have a mixture of these, but then what else would we introduce now? We would have to have a hydride shift, which would give us that. And then the water would come in and attack from this side. And then we would do a proton transfer to get rid of the oxonium ion to give us that product. So if this was our reaction condition, this molecule here, we would have a mixture of this, these two, and this one. But which one would be the major product? This one would have to be the major product. Why? Because it came from a more stable tertiary carbocation versus the secondary. The secondary carbocation gave us these products right there, and then the tertiary gave us the major. Same principles, just different products. Isn't that cool? So we've seen this reaction already where you take this alkene and treat it with some water with a catalytic amount of sulfuric acid, right? And we said that we are going to get a mixture of products, and this one right here is going to be the major because it originates from a carbocation rearrangement from the secondary carbocation to a tertiary, right? Well, what if we don't want rearrangement to occur at all and just have this as our product? What if we wanted this as our major product and this doesn't form at all? There is a way to do that, and there's a named reaction, and that's called the oxymercuration. So, okay, I'm cutting off a little bit, so I need to lower it down. Oxymercuration, like mercury, there. Oxymercuration-demercuration. Is it all on the board? Okay. So the reaction that we want to do is the oxymercuration-demercuration. And what we're going to add in order to get that to occur is it requires two steps, or what's a better way? Two reactions. So you're going to do one reaction, and I'm going to represent that by the number 1. So the first reaction that you're going to do is you're going to treat it with, what's the name of it here? Mercuric acetate. Mercuric acetate looks like this. So we have our mercury and then our acetate like so. So there's our mercury species. And you need some water. Okay? And then the second step, okay, is you treat it with sodium borohydride, like that. If you treat this alkene with these two reactions here, we have our mercury acetate, or we could call it mercury diacetate, and water, and our sodium borohydride, we will generate this only as our product. Okay? Now, stepwise, what's going to happen here when we do this? You can also see that this is the Markovnikov product, right? So that's a good thing. So the key about this reaction right here is there's no carbocation rearrangement. So after you do the first step, this is what you generate right here. Okay. Let me show you here. After the first step, you're going to generate this molecule right here. you will generate OH. Where's my, there it is. Mercury OAC. Okay. So after the first reaction, this is what you generate. And then the second step is the demercuration with the sodium borohydrate, and that just chops off this metal piece to give us, it chops off that metal, the mercury, and replaces it with the hydrogen right there to give us our product. So you can see this and this is the same thing. Okay, now how does it go about doing that? Well, the mechanism is going to show us how that occurs. So I just want to give you the pieces first of how it's going to proceed without showing you the mechanism arrows. And now we will go to the mechanism. Okay? And the mechanism is going to show us why there's no carbocation rearrangement and why that's so important. Now, in order to understand this reaction, we need to understand this reagent right here. And I misspoke when I called it mercury diacetate. It's just mercury acetate. To be more precise, it's mercury 2 acetate, meaning it's mercury 2 acetate, like that, okay? So what does that look like? Well, you're going to have mercury attached to 2 acetate molecules, like so, okay? Now, what does acetate look like? What's that? That's going to look like, so this, I could also have drawn it like this, like that. So right there, that's our acetate piece right there, okay? So this and this are the same thing, but we are going to abbreviate it just to make life a little slightly easier, okay? So when you take the mercury acetate and add it into some water, okay, what's going to happen is it's going to break apart. It's going to break apart into that. Mercury plus our acetate ion there, like that. Okay, so that's what's going to happen when you place the mercury acetate into water. It breaks apart into this, and what's so good about that is this is a very strong electrophile, very, very strong. And so the alkene now can react with the mercury species. Okay. Let's see. And we could call this guy a mercuric cation. Okay. We can name it that, or so our mercuric cation is going to react with our alkene. So let's take a look at how that's going to proceed, okay? So what's going to happen is we have our alkene right here, which is electron rich. And now we have, what do we have here? We have our mercuric cation here, like so, and that's positively charged, okay? But it also has a lone pair there, which is going to be important to understand. Now, what's cool about this mechanism here is that it's very similar to, let's say, it reacting with an acid. What's the mechanism? We have this, and it attacks. So kind of the same idea here. This is going to come in and attack because it's very electrophilic. But what's interesting, at the same time that the pi electrons in this double bond come in and attack the mercury atom, the lone pair on the mercury comes in and attacks there. So what does that give us? It gives us a species that looks like this. So here's our mercury. I'll draw the O-acetate there. And then we have something that looks like that. Right? And so now our mercury is still going to be positively charged right there. Right? So this species right here, we see that it's a three-membered ring right there. And we're going to call that the mercuric. This is so, the word is just so hard for me to say. It's weird. Okay, so let me write it down. That's a C. There we go. There. The mercurinium ion. That's what that three-membered species looks like, or is called, okay? So we have our ion there. Now this three-membered ring prevents any carbocation rearrangement. That's the cool thing, okay? Because when you compare it to the other one, to the other reaction, remember how you treated it with the hydronium? And it went like this. And what did we generate? We generated a secondary carbocation that would then rearrange. Do you see here, when we use the mercury, the positive charge is not on any of the carbons. So that's key. So it's not going to rearrange. Okay. Now the next step in the mechanism, so this went to there. The next step in the mechanism is water reacting with the mercurinium ion. So the question then is, does it attack this carbon? I'll call it carbon 1, or carbon 2. Because we have a weak nucleophile. So which one does it attack? And the answer, I already showed you the product after the first reaction. This water molecule comes in and attacks carbon 1, and then the carbon-mercury bond breaks. And that's going to give us this product that I'm going to draw over here. That's going to be positively charged. And then we have our mercury acetate here. Like that. Okay? And then we are going to do a proton transfer. Okay? A proton transfer. The proton transfer is now going to get this oxonium ion here to get rid of that positive charge. Now, how would we do that? Well, there's a lot of water present. Okay? A lot of water present. So we could envision a water molecule acting as a base going to come and do this proton transfer to give us this. OH, mercury. Okay. So that is the product after the first reaction. Now we need to rationalize and figure out, why did the water attack carbon 1 and not carbon 2? That's what we need to figure out. And so I'm going to pause the video, erase the board so we can talk about that. So the mercury ion here, the way I've drawn it, shows that mercury has 3 bonds. But in reality, when mercury has these 3 bonds, it's very, very unstable. And it more looks like this. We could let's look at 2 options here, okay? We could have mercury that looks more like this, where it's a solid bond there and a dotted bond there. So it's kind of a partial bond. And so when it's a partial bond like that, what we're going to have now is a partial positive on mercury and a partial positive on the carbon. Or we could have a situation, I have to draw it a little bit smaller here, where we have our mercury, where that's the solid line and then that's the, okay. So that would still have a partial positive and that would have a partial positive, okay. Now, comparing these 2 possibilities, which one is the more likely structure? Well, when I take a look at this carbon right here, okay, I see that this carbon is bonded to 1 carbon. So that's kind of like a primary carbocation. Or we could say that's kind of like saying that's a partial primary carbocation. That's probably a better way of saying it. But then when I take a look at this partial positive here, I could say, hey, that partial positive is kind of like a partial secondary carbocation. So when we compare these 2 scenarios, just based off of our understanding of carbocations, we know primary carbocations are very unstable, don't form, and secondary carbocations are more stable. So if we say or bring those principles into this situation and just look at the partial charges, we can clearly see that this partial charge right here is going to be more prevalent than that partial positive because this partial positive here is more stable. And it's more stable because it has more alkyl groups attached. So what we have here is only this one. And because that has a partial, the majority of the partial positive or the partial charge is going to be on this carbon. So when you take your water molecule that is a weak nucleophile, we could say very electron poor, not so electron poor. Where's this electron-rich species going to be attracted to the most? It's going to be attracted to the carbon that has the larger partial positive. And so we could represent that kind of like this. This carbon right here would have a much larger partial positive than that one because of the stability from the alkyl groups. So what's going to happen is that the water is going to be attracted to that carbon. So in oxymercuration reactions, when the water does the attack, okay, so in this step right here, when the water comes in to do the attack, it's going to go for the more substituted carbon. And then the carbon that's attached, the more substituted carbon that's attached to the mercury, that bond has to break. And so that would give us our product after reaction 1. Okay. And that would give us that species right here. And then you would do a proton transfer to take off one of those protons to give us our neutral product. And there's going to be some lone pairs there. just like that. Okay? Now the next reaction, I want to double check one thing here. In the next reaction, or reaction 2, is sodium borohydride. Now the mechanism for that is a radical mechanism, so what we think. It's kind of still not 100% sure, but we know what the end result is. And the end result is when you replace that, or when you react to this species with sodium borohydride, and sodium borohydride is what's called a reducing agent. Okay? Sodium borohydride is going to reduce our compound here. Let's not run out of room. You see how it's going to replace the mercury with what? The proton. And so that right there, this structure right there, is our product. So the moral of the story here, and the cool thing about the oxymercuration, is the fact that there's no carbocation rearrangement. So you get your one product. So brief recap of what we've learned so far in regards to putting water across the double bond or a hydration reaction. We have acid-catalyzed hydration, where we see that we get a mixture of products. Then we do the oxymercuration-demercuration reaction, in which we get one product. Now, we definitely can have the enantiomers. That will be at equal concentration. Now, we have a third reaction that we can talk about that's really, really cool. And that's when we take the same compound. I'll show you the reagents in a minute, but look at what happens here. What we're going to generate is an Anti-Markovnikov product. You see how when we're looking here, from here to here, the OH, or the hydrogens go where Markovnikov predicted they would go. The hydrogen went there. And then in this product right here, where did the hydrogen go? Right there. Markovnikov product, right? But look at this reaction right here. Where did the hydrogen go? It went right there. So this is the anti-Markovnikov product. And how do you get an anti-Markovnikov product? That is when you do a reaction that's called the hydroboration-oxidation. That's the one word right there, hydroboration. I don't know why I made it look like that. So we have hydroboration-oxidation reaction. And this is another two-step reaction in which you are going to, in step 1, you're going to treat the alkene with a borane, BH3, that's called borane. And then you're going to treat it, and it's going to be in a solvent called THF. And THF stands for tetrahydrofuran. It's just a common organic solvent. Okay? So that's not too terribly important here. Well, I retract that. Okay, it needs to be in THF. And then 2, the second step is the oxidation step. And the way you're going to do this oxidation is with peroxide, H2O2, and some base. So the hydroboration is the first reaction, and then the oxidation is the second reaction. And when you have to do both of these reactions in order to convert this alkene into this alcohol. Now I want to take a moment to say, hey, it would be a great idea for you to create your notes in this fashion. Create it based off of functional groups. So you will have a page in your notebook that says something to the effect, how to make alcohols. Because look, alcohol, alcohol, alcohol. 3 different ways. So I would make a list in that section, how to make alcohols. Well, you can take an alkene and treat it with these different reagents. And then as we progress through the semester and into Orgo 2, you will learn even more reactions on how to make alcohols. And you'll just keep adding to that list. So this would be a really good idea to kind of categorize your reactions based off of what they make. And the functional groups here are alcohol. So how do you make alcohols? Here's 3 ways up to this point. Okay? Now let's delve into what's similar and what's different between these 3 reactions. And the first thing that we've noticed that's different is hydroboration-oxidation reactions are anti-Markovnikov. And so I think that's so cool because you have the same starting materials, okay, but you're going to get 3 different types of alcohols. You could get this one, or these guys, or this one. You can see where the alcohols are at different places. So cool. Okay. Another factor that we need to be aware of is the stereochemistry. So if we treat that with our borane right here, THF, and step 2, the oxidation. Okay. The stereochemistry is really important. But can you pause the video and tell me where the alcohol is going to go? Is it going to go on carbon 1 or carbon 2? What do you think? Well, it's going to go to the less substituted side. So we're going to have the alcohol go here. Okay? So that's the regiochemistry, right? The oxygen atom is going to go to the less substituted side. Or we could say the hydrogen adds anti-Markovnikov. So this is the anti-Markovnikov product. But what is about the stereochemistry here? And that's the cool thing about this reaction, and some kind of unique to it, is the way that it adds is you'll notice that the hydrogen that is being added and the alcohol that is being added are on the same side. They're both wedges. So yes, this is an addition reaction. Yes, it is also called a hydroboration-oxidation reaction. But then we could say, hey, what type of addition reaction is it? And we call it a syn-addition. A syn-addition is telling us that the 2 groups that are being added, and in this case it's a hydrogen and an alcohol, are on the same side. Okay. Now you could have very well, because what's interesting about this reaction is the fact that these carbons right here are sp2 hybridized. So that means they're flat. So if I take this molecule, okay, well, it's going to be hard to draw on the board, but if I take this molecule represented by my hand, okay, and I take it and I rotate it like this, okay. Now my thumb, I want my thumb to represent this methyl group right here, okay. When I take it and rotate it, do you see how the methyl group's pointing towards my chest? Okay. If I represent the molecule like that, okay, these carbons right here, represented right here, we have empty p orbitals above and below my hand. So when this reaction occurs, the reaction can occur on the top of my hand, which is represented by these wedges, or the reaction can happen underneath my hand. And so if the reaction happens underneath my hand, then we would have something that looks like this. You can see that they're both syn-addition because the hydrogen and the alcohol are the same on the same side. They could either be both wedges or both dashes. They're both syn-addition. The only difference between these two is the approach of the reagents. Is it from the top or from the bottom? What you will never see with hydroboration oxidation is a product that looks like this. Like that. Is this still an addition reaction? Yes, it is, because we've added a hydrogen and an alcohol across that double bond. But this is called an anti-addition. And you do not have anti-additions with the hydroboration oxidation. That is very, very important to realize. Okay? I want to end this video on just understanding why hydroboration is syn-addition and the regiochemical outcome. Why is it Anti-Markovnikov? And it boils down to the fact that boron, the boron atom in borane right here, it's just a tricky bugger. It just is weird. It's a Lewis acid, okay? So borane, we have boron right there. We're going to have our H here, and another H here. And this is, it's sp2 hybridized because it's flat. It's trigonal planar. So it has a p orbital. And you can also see with borane that it only has 6 electrons. And we've been taught that, hey, all atoms want to have an octet, right? Boron is weird in the fact that it's content with 6, but it still is like, I need 8, I need 8. And so it's going to react to get 8 electrons around it, but the moment it gets 8, basically what it's asking for, it's like, I hate this, and it spits it back out. And so borane, or boron, the boron atom is just a finicky element. And so because of its finicky-ness, it helps us understand the reactivity of certain things. So let's take this molecule right here, okay, like this, CH3. What I want to do is I'm going to take that cyclopentane ring right there, and I'm just going to tip it 90 degrees. Okay, so if my hand represents the ring, my thumb represents the methyl group, and I just tip it like this. Okay? That's what I'm trying to represent then is it's going to look something like this. Okay, it's going to be, that methyl group right there is going to be pointing out at me. Okay? When I just tip it like so. Okay, now we need to make sure that we understand that we have a double bond here, okay? So what happens is because, let's see here, make sure there's the double bond. There we go. Now, when we look at it this way, the borane molecule can approach from the top or from underneath, okay? Now, the way that it approaches is very, very important because let's contrast two different approaches here, okay? Let's do it like that. Okay, let's consider two different approaches here. Okay. And this. So borane could approach like this, right? And let's get a different color here. It's going to approach something like this. So we have BH2, and I'm going to extend one of the hydrogens like that, versus the opposite, BH2 with the hydrogen extended like that, okay? Now what's interesting is borane is a Lewis acid, so it wants electrons. And we see the alkene is electron rich. So the alkene is going to attack the borane. So we could see it like this, BH3. So this is going to come in and attack it, just like that. Okay? But then what happens when that attacks? Okay? When it attacks like that, what are we going to generate? We are going to generate a carbocation. So when that reacts like that, sorry, let's keep it like that. All right. We are going to generate, hey, what if the borane, I need to draw this up a little further. Okay, so let's say the borane goes there, BH3, okay, minus, and then there's a plus right there, okay? If that's the case, we generate a carbocation, right? And then we can start having rearrangements. But hydroboration-oxidation doesn't do any rearrangement. So this isn't right. And the reason why this isn't right is because, like I said, the moment the boron atom accepts 2 more electrons to have an octet, it's like, I hate this. And it's like, no, I don't want it. And so the mechanism, how it reacts, is very, very interesting in the fact that if I show it here now, what color should I use here? So when these pi electrons come in and attack boron, like so, it's like, oh, this sucks. And then so instantly it breaks this boron-hydrogen bond and donates it down. And so what does that do for us? Is it generates this product right here. All right. And we are going to have what? Get my colors here. There's our methyl. Right? What's going to happen is the boron is going to be like that too. And then that will be our hydrogen. Do you see how the boron and the hydrogen add to the same side? And it's adding to the same side because the moment the pi electrons come and attack the boron, it just gets all upset and just drops the hydrogen down to get back to only 6 electrons around the boron atom. And so that just happens so fast, it's concerted, that it adds in a syn-addition, like that. Okay? But now, the next consideration that we need to talk about is why does it add this way instead of this way? Okay? Why does it not do this? Okay? Because remember, these hydroboration-oxidation reactions are regioselective. Remember, if we did this reaction right here, what would our product ultimately be after we do steps 1 through 2? All right, we would have the alcohol would go on the less substituted side. It would be the Anti-Markovnikov, and the hydrogen would be added there. So in order to explain that, we can talk about it via electronics. Electronics can help us understand that, and sterics. And due to the length of this video, we will stop here and we'll pick that up in class as to why is the hydroboration oxidation reaction regioselective?